Hey guys, we're back continuing where we left off. Sorry this had to split into two videos, but when we look at the powers being the same, we have a cube on top, a cube on bottom. Imagine plugging in a really big number like a million, right? A million cubed, a billion cubed. It's going to make a really big number. When we take that number times 4, take that number times 3, we still get a ratio of 4/3. So we still get a limit as x goes to infinity of 4/3. So if we see the powers are the same top and bottom, we just can look at the coefficients of those bigger powers, divide them, and we get 4/3. Okay. Similar with limit as x goes to negative infinity here would be the same thing as 4/3. Okay. So it's pretty easy to see what's more powerful when we have polynomials like this. But we have like a hierarchy of power that I want to talk about real quick. So our most powerful are exponentials. So things like e to the x, 3 to the x, 5 to the x. As long as the base to that power is bigger than 1, that's always going to be our most powerful. Kind of our mid-tier are our polynomials. Things like x cubed, x to the fifth. Even if you think about square root x, we want to think of it as x to the 1/2 power, things like that. And then our least powerful are logs. So if we have a rational function, right? If we have an exponential and a polynomial, exponential is always more powerful. If we have a mid-tier, right? If we have a polynomial and a log, the polynomials are going to be more powerful. Okay? So that'll help us. We'll see problems like that in class. All right, I want to talk just quickly about the squeeze theorem here. Okay, so here's how the squeeze theorem works. If I have a function, f of x, and black is going to be f of x. Red is going to be g of x. And blue is h of x. Okay, so what you notice here is that f of x has a value that's always squeezed in between g and h. Sometimes this is called the sandwich theorem. So f of x is always in between g of x and h of x. Okay, so if we know something like this, if you know that f of x is always greater than or equal to h of x, but always less than or equal to g of x. Okay. If we can squeeze f of x in between those two functions, we know that f of x is always between those two functions. And we know two things. Let's call this point C. We'll call this capital L. if we know that the limit as x goes to c of g of x equals some number, and the limit as x goes to c of h of x goes to that same L value, then by the squeeze theorem, we can say that the limit as x goes to c f of x must also equal L. So basically what this is saying is if you can say that a function is always in between two functions, and those two functions have the same, right, the top piece of bread and the bottom piece of bread have the same limits, then your function f of x must also have that same limit as well. Okay, that's the squeeze theorem. We'll talk about how we use that in class a little bit. It can be a little bit tricky. I also want to talk about that conjugate problem. So I'm just going to write a new one and solve it for you, just so you can see our methods of solving limits so far. We can factor and cancel, plug in. We can expand, cancel, and plug in. But we can also use the conjugate. Here's an example. I'll do a different problem than the one from over. We'll do the limit as x goes to 0 of, let's say, x over square root of 16 minus x minus 4. So a little bit different than the one before. But we see if we plug in 0 for x, we get a 0 in the numerator. And when we plug in 0 for x in the denominator, 16 minus 0 is 16. Square root of 16 is 4. 4 minus 4 is 0. So we get 0 to 0. So we know that there's a hole here. So we know that the limit should exist. We can solve this limit, okay? We can solve this limit by multiplying by the conjugate. The conjugate is this term, but I just alternate that sign right there. Not the one that's inside of the radical, but the one that's between the radical and the constant. So I'm going to multiply both the top and bottom here. I'm going to multiply the top and bottom by the conjugate, root 16 minus x plus 4. Root 16 minus x plus 4. Conjugates are an effective way to rationalize. They get rid of a square root. And when we FOIL this thing, it ends up being really simple. So here's what we do. First off, that x on top, that's one of the things I'm trying to cancel. So I'm going to leave the top factored out like that. I'm not going to distribute this x right here. I'm not going to distribute it. I'm going to leave it as x parentheses root 16 minus x plus 4. And on the bottom here, I'm going to just FOIL this. Root 16 minus x times root 16 minus x is simply 16 minus x. Okay. The next two terms, 4 root 16 minus x and negative 4 root 16 minus x, are going to cancel each other. So I'm not even going to write them. And then I have to do the last term. Negative 4 times positive 4 is negative 16. So simplifying the bottom, I see a minus 16 and a positive 16 that can cancel. Don't forget about that little guy right there. So what I'm left with then is x parentheses root 16 minus x plus 4 over negative x. Well, now I can cancel the x here and the x here. So now I've got root 16 minus x plus 4 over, again, I don't want to forget about this, negative 1. And again, I'm performing a limit here. After I cancel, I want to plug in 0. When I plug in 0, I get 16 minus 0 is 16. Square root of 16 is 4. 4 plus 4 is 8. And I got 8 divided by negative 1, which equals negative 8. So you can use that to help you with that stretch problem at the end of the last one. All right, guys, sorry for this being over 2 videos. You just need it in your notes once. I'll see you guys tomorrow. Bye.